About the combustion analysis, which is a form of gravimetric analysis. So combustion analysis usually entails this type of a setup that we see here. Okay, so what we'll do is we have a furnace that inside that furnace there's a sample that we put your sample in, whatever it is. It honestly could be potato chips or in this example maybe we're going to use coal. All right, so coal is used to power plants. All right, and so the molecular formula for coal is something like this. It's C137H97O9NS. Okay, so we can put coal in our combustion analysis chamber in our furnace here, right? And if we add lots of oxygen, right, we funnel in oxygen through and heat up that furnace, the coal will undergo an oxidation reaction, right, to form. So if I look maybe here, so our coal plus oxygen yields, we're going to make from the carbon, we'll make carbon dioxide, CO2. From the hydrogen, we'll make water molecules, H2O. Right? So carbon makes us CO2, hydrogen gets us H2O. This oxygen honestly gets spattered in a little bit here, a little bit there, right? We're also fueling in excess oxygen here. So it's really actually hard to follow the oxygen, so we don't ever follow them. But this nitrogen and this sulfur make these compounds what we call NOx and SOx. So NOx is either NO2 or NO3. Covalent compounds, not the polyatomic ion form. And these molecules are pollutants, and SOx are usually SO2 or SO3. Okay, and remember those are gases, again, not the polyatomic ions, we're talking about the covalent compounds, and these are pollutants that we can breathe in our air. They're actually very dangerous and toxic to us in high quantities, which is why burning coal is not good for, well, it's not good for our breathing, our pollution, the pollution, it's dangerous to our health. Okay, so it's that NOx and SOx. So anytime you combust a carbon atom, it's going to form carbon dioxide. Anytime you combust a hydrogen atom, you're going to get this water molecule. If nitrogen's in the formula, you'll get NOx, and if sulfur's in the formula, you'll get these SOx compounds. Okay, that's pretty much where we're going with that. All right, but so in this, in our apparatus up here, right, we've got our furnace with our coal in it. It's heating it up really hot, and eventually the coal is starting to combust. Then that air or the oxygen that passes through is some of it's going to carry away some of our gaseous products, which would be that carbon dioxide, the water, the NOx, and the SOx. So as those molecules funnel into what is the water absorber, so this like part of the combustion analysis apparatus has these, they're like beads that are able to absorb only the water molecules. Okay, so after the analysis is over, the mass of the beads will increase, right? Because it'll absorb any of the water molecules that were made over here. And what we just learned is that any water molecules come from the hydrogen being combusted. Okay, so remember, all these products still keep funneling through. The water's pretty much been absorbed, though, by this water absorber. And next up, you have a carbon dioxide absorbing compound. So all those gases filter their way through, and again, these like beads, they absorb and pull out all of the carbon dioxide from your equation. And remember that any carbon dioxide in your equation is coming from any carbon in your molecular formula, right? So then on the way out, you see unreacted oxygen gas and other gases, and in our case of coal, you'll see the NOx and the SOx kind of come out through the end. But essentially, what you really get from these combustion analysis reactions is you get the mass of water, and remember the mass of these beads is also going to increase because it absorbs any carbon dioxide. So you see an increase in the mass of beads, but you're able to deduce what is the amount of carbon dioxide that was produced and what is the amount of water that was produced, okay, from these combustion reactions. So if we look at a sample problem, this is kind of where you see the sample problem, how it plays into the combustion analysis chamber. So 2.15 milligram sample of polystyrene, a hydrocarbon. Breaking down that word, it means it's only made up of hydrogen and carbon atoms. Okay, so a hydrocarbon, so it's hydrogen to something, carbon to the something. So anyways, a 2.15 milligram sample of polystyrene produces 7.26 milligrams of CO2. I'm going to write that down here, 7.26 milligrams of CO2 and 14.8 milligrams of H2O, okay, during that combustion analysis. So again, the water was absorbed by the beads, the carbon dioxide was absorbed from a different set of beads, and you were able to determine how much mass of carbon dioxide and water was made from that combustion of a 2.15 milligram sample that you put into the furnace. Okay? So then the question is, what is the empirical formula for polystyrene? Remember, the empirical formula is the formula that has the least number of the subscripts. It's the least common denominator, right? So we're looking for empirical formula. And when we're solving for these problems, what you're going to want to do is you're going to want to convert the mass of CO2 to moles of carbon, and you're going to want to convert the mass of H2O to moles of hydrogen, okay? Because these are the amount of moles that were in your original sample. Then if you look at the ratio of the moles of carbon to the moles of hydrogen, you could figure out what's that empirical formula. Are they 1 to 1? Is it 2 to 1? Is it 3 to 1? So on and so forth. So when we're kind of approaching these questions, that's what we're going to want to do. We're going to want to take the mass of carbon dioxide and convert it to moles of carbon, and the mass of water and convert it to moles of hydrogen, and then figure out what's the ratio between these two, and that should lead us to fill in that empirical formula. Remember, it's a hydrocarbon, which means it's carbon to the X, hydrogen to the Y. That's all. It's just a compound made of only carbon and hydrogen. So if we're looking at our dimensional analysis, let's do our carbon dioxide first, okay? So let's see. So if I do it, maybe let's do a little concept map first. So CO2. So I'm starting with milligrams of CO2. I need to get to grams, right? Because I'm going to have to get to moles of CO2 and then convert moles of CO2 to moles of carbon. All right. So milligrams of CO2, grams of CO2. All right. Milligrams to gram conversion. That's that 1,000-fold. Right, that's from our brain. We just know that there's 1,000 milligrams in 1 gram. Grams to mole conversion, that's where whenever you need to convert between mass and moles, you have to use the formula weight. And when we're converting between moles of CO2 and moles of carbon, we need a stoichiometric factor, stoic. I'm gonna write stoic there, okay? And if we look at CO2, we see that for every 1 molecule of CO2, it's got 1 carbon atom and 2 oxygen atoms. So actually the stoichiometric ratio for how many moles of carbon are in this many moles of CO2, it's actually 1 to 1, right? Because in every 1 molecule of CO2, it's made up of 1 carbon and 2 oxygen atoms. All right, so there's your 1 to 1 ratio. So that's the concept map kind of behind where we're going. So let's put the dimensional analysis table. Let's fill in our numbers now. So we're starting off with 7.26 milligrams. So 7.26 milligrams of CO2. I'm in milligrams. I got to get to grams. So there is 1,000 milligrams in 1 gram of CO2. Milligrams cancel. Now I'm in grams of CO2, I need to get to moles of CO2. So grams to mole, I need formula weight to do that. So the formula weight of CO2, you'd have to do a quick on the napkin calculation. Carbon's atomic mass is 12, oxygen 16. I got 2 16, so that's 32. 32 plus 12 is 44 grams per mole. Okay. I don't expect you to be able to do that as quickly as I did. I've been doing this for a while. I'm also a biochemist, and we really, we work a lot with carbon, oxygen, nitrogen, hydrogen, sulfur, phosphorus. So I tend to know all the molecular weights of those compounds. But that's where your LOA cheat sheet comes into play, right? It's got the periodic table. You find the mass of carbon, the mass of oxygen, and you can solve for it that way. But there's our formula weight for carbon dioxide. So 44 grams of CO2 and 1 mole of CO2, right? Remember, when we take these equations like 44 grams per mole, we can make that into a linear mathematical a relationship by saying 44 grams is equal to 1 mole. And then when we see these, we can easily plug those in, right, for in our dimensional analysis tables. Okay, but back to our math. All right, so now we're in moles of CO2. Now I gotta get to moles to carbon. And remember, I said it was a 1-to-1 ratio because for every 1 molecule of CO2, there's 1 molecule of carbon. So 1 molecule of CO2 is 1 molecule of carbon. And moles and molecules are pretty much exactly the same thing, right? They're both amounts. There's just a lot of molecules in 1 mole. So moles cancel, grams cancel, and I'm left with moles of carbon. So if I do quick mathematical calculation in my calculator, I would do 7.26 divided by 1,000 divided by 44 times 1, and I get 0.000165 moles of C. Now I have to do it for H2O. All right, so H2O, we're going to do our dimensional analysis. Put it over here. What's my starting amount of H2O? It is 14.8 milligrams of H2O. I need to convert milligrams to grams. I pretty much have to follow this same follow kind of this same outline that I did up here, but now I just need to think about it in terms of hydrogen, right? So, milligrams to grams of H2O. So there's 1,000 milligrams in 1 gram of H2O, right? I have to convert grams to moles, and I'm going to need the molecular weight. So H2O, hydrogen weighs about 1 gram per mole, oxygen weighs 16. I've got 2 hydrogens, so 2. So 16 plus 2 is 18. So 18 grams for every 1 mole of H2O. All right, grams of H2O cancel. My milligrams have canceled. All right, now I'm in moles of H2O, and I have to get to kind of like where this step was here. Moles of H2O, I got to get to moles of hydrogen. So if I have 1 mole of H2O of water, how many moles of hydrogen are in 1 mole of H2O? And the answer is 2, right? It's 2 hydrogens and 1 oxygen. So 2 moles of hydrogen. Get rid of that right there. And moles of H2O cancel, and I'm left with moles of hydrogen. All right, so then we grab our calculator. We do our calculations. 14.8 divided by 1,000 divided by 18 times 2. And I get 0.00164. This is what I thought was going to happen, is that I might read the question wrong. So let me just check the amounts that I was supposed to have. It should be a 1.48 milligram sample, not a 14 milligram sample of water. Oh, all right, so I apologize profusely, but this number, my starting number here was incorrect. It should actually be 1.48 milligrams, not 14.8. So let's recrunch that number. Okay, let me erase that final answer. Nothing changes as far as the dimensional analysis is concerned. I just needed to tweak that first number. So 1.48 divided by 1,000 divided by 18 times 2 equals, get me back in a pen here, 0.000164, right, moles of hydrogen. Okay, so that many moles of hydrogen and that many moles of carbon. And off the bat, you can tell they're practically the exact same number. 3 zeros, 165, 3 zeros, 164. So when we look at the ratio of carbon to hydrogen, we can take and divide the mole. So 0.00165 mole of carbon divided by 0.000164 moles of hydrogen. That's going to equal 1. It's a 1-to-1 ratio, right? So 0.000165 divided by 0.000164, and you get 1.006. And so it's a 1-to-1 ratio. So the empirical formula, remember we said it's C to the X, Y to the Y, it's going to be 1-to-1. So our empirical formula is C1H1 or CH. Okay. So that is how we can use combustion analysis to help us solve for empirical formulas. Now remember, in some of your homework problems, it's going to ask you to get the molecular formula. So the molecular formula, remember, to solve for once you know the empirical formula, you can take the molar mass of the empirical formula and divide that into the molar mass of the molecular formula they give you, and it'll give you some coefficient, like a whole number ratio. And then that's what you would go through and multiply each of these subscripts by to get your molecular formula. Okay, we've worked some of those problems before. I'll work some more on Thursday. So if that sounded confusing, come on in to Thursday or Zoom in and we will work those problems for you. All right.